Welcome back to Bugged Out. Now, normally this is when I'd introduce one of our outstanding guests, architects, verification experts, tool innovators, and folks who keep silicon moving forward. But to close 2025, we're doing something different. This is FutureCast 2026, a two-part holiday series where I step back from the interviews, reflect on where the semiconductor industry truly stands, and share my predictions for the year ahead and the years after. We'll return to our regular guest lineup after the holidays, but for now, it's just you and me. So let's delve into part one, where silicon stops behaving like a finished product. Anyone who's been in this industry long enough can feel it. The center of innovation has moved. The breakthrough actions isn't happening inside the transistor, it's happening above it. And yes, people love to proclaim Moore's Law is dead. I put it like this: Moore's Law isn't dead, it's just working remotely and checking emails less often. Transistors still improve, but the economic engine behind predictability scaling is gone. Progress now comes from assembling smart, more tightly integrated systems where logic, physical, packaging, memory, and software all interact. The biggest performance gains today come from disaggregating designs into chiplet-style components. Now, mostly used within closed company-specific ecosystems today, but steadily gaining traction. Hybrid bonding pulling memory dramatically closer to compute. HBM or high bandwidth memory redefining bandwidth ceilings. Photonic interconnects stepping around electrical limits. Coherency fabrics tying dies into unified engines. And by 2030, we'll start seeing the first early chiplet vendors, limited, curated, but real. Let's talk about the collapse of the 1990s orthogonalization. For decades, we scaled complexity by separating concerns. Logic over here, timing over there, thermal somewhere else, packaging and software in their own corners. But in a multi-die world, thermal drift affects latency. Inter-die timing affects coherency. Photonic links shift bandwidth with temperature. Software loads drive physical behavior. Chiplet integration introduces new cross-vendor interactions. These aren't packaging notes anymore. They're functional behaviors, and that means they're verification problems. So why does this matter for verification? Verification now must reason across physical plus logical, multi-die coherency, cross-die timing, workload-driven variation, multi-vendor components, emergent system-level behavior. This is where digital twins become essential, and I mean the real kind, not the buzzword kind. A true digital twin is hybrid: simulation for correctness, emulation for real workloads, prototyping for speed, physical solvers for thermal and stress. No single engine captures the truth. The twin only works when the engines converge into a consistent view of the system. That is the direction the industry is heading, and exactly the kind of integrated verification philosophy you see reflected in Questa 1, where the goal is to unify verification rather than scattered across silos. Next, I want to unpack one of the biggest shifts in modern silicon. What happens when the hardware keeps evolving after it ships? For decades, hardware followed a familiar, comfortable life cycle: design, verify, tape out, ship, and retire. The systems your customers ran looked exactly like the one you validated. But today, that idea is nostalgic. AI models update monthly. Security vulnerabilities appear weekly. Workloads shift constantly. Users' expectations move at the speed of software, not silicon. To survive that mismatch, products become software defined, continuously updating firmware, drivers, orchestration layers, and sometimes even entire AI models. It's like your hardware wakes up each morning asking, "Who do I want to be today?" And the silicon responds, "Did anyone verify this first?" So why do software-defined products disrupt traditional verification? What's new is this: hardware behavior is no longer static. not because silicon changes, but because the assumptions around it do. Correctness depends on workloads and evolving models. Build updates change system behavior. Failure arises from runtime variation rather than design bugs. This is the evolution: traditional verification plus lifecycle verification. So, how will teams actually solve this? Here's where we must be practical. No engineer is verifying millions of devices or weekly model updates manually. Instead, teams will rely on digital twins as proxies for the deployed fleet. They model real workloads, real thermals, and real behavior. You test against the twin, not the product in the wild. Verification intent carried forward. The same constraints, assertions, and coverage goals you created for pre-silicon don't disappear. They become part of the post-development verification fabric. Automation plus agentic workflows. When the update rolls out, the infrastructure automatically runs relevant regressions, checks safety envelopes, validates model behavior, replays critical workloads, reports deviation, and blocks any updates that fail. Unified verification environments, bringing engines, data, intent together so verification stays consistent across the entire lifecycle, not stuck in an isolated silo. This is the only scalable model, and it's why software-defined products don't burden engineers. They shift effort from manual testing to automated verification ecosystems. So here are my predictions related to part one. By 2026, multi-die verification becomes unavoidable for advanced ICs. Lifecycle-aware verification becomes mandatory for advanced AI-driven devices. By 2030, hybrid digital twins are essential, and chiplet vendors enter the market with early offerings. Also by 2030, runtime verification and live digital twins become standard system-level infrastructure, just as simulation and emulation are standard IC-level infrastructures today. That wraps up part one of FutureCast 2026, a look at how innovation has moved above the transistor and why hardware can no longer stay still after it ships. From multi-die architectures to software-defined systems, the story is the same. Verification is stretching across the entire lifecycle, and the boundary between design and deployment is dissolving fast. In part two, we'll go deeper into the forces shaping what the system can ultimately become: specialization, the data movement bottleneck, power ceilings, security boundaries, and the rise of agentic AI. Thanks for joining this special edition of Bugged Out. Stay curious and keep building the future.